Dear learner, I welcome you all on the MOOC, that is Emerging Technologies and Renewable Energy. I am Sanjay Agarwal, Professor and Pro Vice Chancellor of Chhattisgarh Swami Vivekanand Technical University, Bhilai. Dear learner, in this particular session, we will discuss heat transfer characteristic of surface. After that, we will discuss radiative properties of the real surface, and after that, we will be able to understand the concept of the solar radiation and how to estimate solar radiation on horizontal surface as well as tilted surface. As you know, all the solar energy devices depend upon the electromagnetic radiation continuously being emitted from the sun and striking the earth surface. These are called short wave radiation. When solar radiation strikes the earth surface, it gets absorbed and re-emitted as long wave thermal radiation. Thus, thermal radiation are a form of energy emissions and depend mainly on the temperature and the characteristics of the emitting surface. The various forms of the radiation differ only in wavelength. If you study the spectrum of the electromagnetic waves, the range of the wavelength of thermal radiation is theoretically from 0 meter to infinity. As large part of thermal radiation has wavelength in the range from about 0.1 micrometer to 100 micrometer. The visible portion of thermal radiation range from approximately 0.4 micrometer to 0.7 micrometer. As solar radiation passes through the atmosphere, some of it is absorbed, some is scattered, and rest is reflected by air molecules, water vapor, cloud, dust, pollutants, forest fires, and volcanoes. The radiation reaching the earth's surface is called diffuse solar radiation, or you can say simply diffuse radiation. The solar radiation which reaches the earth's surface without being diffused is called direct solar radiation or simply direct radiation. The sum of diffuse and direct insolation is called Glover insolation. Atmospheric condition can reduce direct insolation by about 10% on clear and dry days and by 100% on thick and cloudy days. The surface of the sun has an effective temperature of approximately 5760 degree Kelvin and emits most of energy between 0. micrometer and 3 micrometer. The surface of the sun has an effective temperature of approximately 5760 degree Kelvin and emits most of its energy between 0.1 micrometer and 3 micrometer. Learner, now we will understand heat transfer characteristic of surface. Thermal radiation are electromagnetic radiations and travel at the speed of light, which is equal to about 3 into 10 to the power 8 meter per second in the vacuum. This speed of thermal radiation is related to the wavelength and frequency of the equation. So here you can say that C is equal to lambda nu, where what is C? C is nothing. Basically, it is a speed of light and generally it is written or denoted in meter per second. And lambda is wavelength of the radiation. It is the unit of this wavelength is meter, and nu is denoted as frequency of the radiation and unit is per second. The electromagnetic radiation have dual nature, behaving like waves and also like particles. As particles, electromagnetic waves are discrete quanta called photons of energy, that is E, and given by this formula, that is E is equal to h nu, where what is E? E is nothing, it is energy of a photon in joules, and h is Planck constant, and the value of this Planck constant is 6.6 into 10 to the power minus 34 joule second, and this nu is nothing, it is frequency of radiation, and you know the unit of frequency is 1 upon second, or you can say per second. When a beam of thermal radiation is incident on the surface of the body, the following could happen. What will happen? Some of it may get reflected away from the surface, some of it may get absorbed by the body, some of it may get transmitted through the body. Here you can see in the diagram also that solar radiation is incident on the surface, some is being transmitted, and some part of it is being reflected from the surface. The radiation characteristic of surface are its ability to reflect, which is called its reflectivity. If its ability to absorb is called absorptivity, and its ability to transmit is called transmittivity. These are defined as, you can denoted by the alpha. So alpha can be denoted as reflectivity, or you can say it is a fraction of radiation reflected by the surface. Then this rho is nothing, it is a absorptivity, and it can be defined as fraction of the radiation absorbed by the surface. The third term, that is tau, and tau denotes the transmittivity, or it can be defined as fraction of radiation transmitted through the surface. So you can write alpha plus tau plus rho is equal to 1. So most of the solid objects are opaque, hence you can say this value of tau is equal to 0, or you can say it will not transmit. So you can say transmittivity is 0. If a body absorbs all the incoming radiation, such a body is called black body. The radiation characteristic of a surface depend not only on the surface properties but also on the wavelength and direction of the radiation. Now here you can see the emissive power, which is denoted as E suffix B of a black body, is expressed by Stefan-Boltzmann law, which is defined as E suffix B is equal to sigma multiplied by T to the power 4, where this sigma is nothing, it is called Stefan-Boltzmann constant, and value of this sigma is equal to 5.67 into 10 to the power minus 8 watt per meter square multiplied Kelvin to the power 4. And this T is what? This T is nothing, it is basically temperature, and the unit is always denoted in degree Kelvin. Now we will understand the radiative properties of the real surface. As you know, an ideal black body is a perfect absorber as well as perfect emitter of thermal radiation. All real surface emits less energy than the corresponding black bodies. Now we will define what is the emissivity of a surface. So the ratio of total emissive power of a real surface to the total emissive power of a black body is called the emissivity of the real surface. The emissivity of real surface is a function of following three parameters. One is surface temperature, another is wavelength of incident radiation, and third one is direction of the incident radiation. The emissivity defined is the average value over the entire wavelength range in all directions. It is called total emissivity. Learner, now we will understand the Kirchhoff's law. The Kirchhoff's law of radiation states that monochromatic emissivity is equal to the monochromatic absorptivity for any surface when in thermal equilibrium with its surrounding. This may be expressed by this given expression, where the first term is at left side is the monochromatic emissivity at the wavelength lambda and temperature T, and the second term, that is on the right hand side, is the monochromatic absorptivity at wavelength lambda and temperature T. Dear learner, you will learn in this course that solar energy absorbed by a solar collector is always in the process of losing the absorbed radiation to the environment by three phenomena. One is a radiation, another is a conduction, and third one is a convection. Now we will understand what is the advantage of selective surface. The radiation losses from a solar absorber can be reduced significantly when the receiving surface has selective radiation properties. Now we will understand the properties of the some selected surface. So here you can see the table. In table, this table is basically defined in the 3 column. Here you can see in the first column type of material is denoted, in the second column short wave absorptivity is shown, and third column long wave emissivity is shown. So just you can read here and you can say that short wave absorptivity of black nickel or nickel plate steel is 0.95 and long wave emissivity of black nickel or nickel plate steel is 0.07. Similarly, the fourth material here you can see that is a black chrome of a copper. So short wave absorptivity and long wave emissivity for black chrome of copper is 0.95 and 0.14 respectively. So here different material has been shown. You can see the black copper on the copper, copper oxide on nickel, copper oxide on aluminum, lead sulfide crystal on aluminum, and here on the second and third column the short wave absorptivity and long wave emissivity of all these material like black copper on copper, copper oxide on nickel, copper oxide on aluminum, lead sulfide crystal aluminum has been shown. So here you can see the following properties of selective surface. One is high absorptivity for radiation in the solar range of wavelength. Second properties is what? That is a low emissivity for long wave thermal radiation. It is highly desirable to make use of selective surface in solar collector absorbers to attain high solar energy absorption and at the same time to reduce radiation losses to the surroundings. Learner, now we will understand the basic phenomena that is called solar radiation. So as you know, the sun emits electromagnetic waves that carry energy. Solar radiation is the energy emitted by the sun in all directions through space in the form of electromagnetic waves. There is no life on the earth without solar radiation. It is directly or indirectly responsible for phenomena such as plant photosynthesis, maintaining a planet temperature suitable for the life, and wind formation. Solar radiation is measured on the horizontal surface by some of instruments, and such instruments are pyranometer, pyroheliometer, sunshine recorder, solarimeter, and the unit in which this solar radiation is measured, it is measured in watt per meter square. So you can say this watt per meter square is a unit of solar radiation. Now we will understand briefly the different instrument, that is a pyranometer, pyroheliometer, which is used for the measurement of solar radiation. So here you can see the pyranometer is a one type of actinometer used to measure irradiance of solar energy within the preferred location as well as flux density of solar radiation. The range of solar radiation extends between 300 and 2800 nanometer. The SI unit of irradiance are watt per meter square. Usually these are used in the fields of researches like climatological and weather monitoring, but current attention is showing interest in pyranometer for solar energy worldwide. Now we will understand what is the working principle of this pyranometer. Here you can see in the diagram also. The working principle of pyranometer mainly depends on the difference in the temperature measurement between two surfaces like dark and clear. The solar radiation can be absorbed by the black surface on the thermopile, whereas the clear surface reduces it, so less heat can be absorbed. The thermopile plays a key role in measuring the difference in the temperature. The potential difference formed within the thermopile is due to the gradient of temperature between the two surfaces. These are used to measure the sun of solar radiation, but the voltage which is generated from the thermopile is calculated with help of potentiometer. The information of radiation needs to be included through planimetry or an electronic integrator. Now we will understand another instrument which is used to measure the solar radiation, that is pyroheliometer. The pyroheliometer is one type of instrument used to measure the direct beam of solar radiation at the regular occurrence. This instrument is used with tracking mechanism to follow the sun continuously. It is responsive to wavelength bands that range from 280 nanometer to 3000 nanometer. The unit is again watt per meter square. These instruments are especially used for weather monitoring and climatological research purpose. The working principle of this instrument can be understood like this. The sunlight will enter in the long collimator tube and will incident on the black absorber plate. The thermopile is in contact with the black absorber plate. When the black plate will absorb the heat, the EMF will generate between the hot and colder surface due to the temperature difference. This EMF will be used to measure the value of beam radiation. Another instrument that is called sunshine recorder. A sunshine recorder is a device that records the amount of sunshine at a given location. The result provide information about the weather and a climate as well as temperature of geographical area. There are two types of sunshine recorder. One is Campbell-Stokes recorder and second one is a Black-Larsen recorder. Another instrument is basically called solarimeter. So solarimeter is just like a simple instrument like a meter, voltmeter. Just you have to put this instrument where you have to measure the solar radiation, and this solar radiation will incident on the top surface of this instrument and it will give you the reading of the solar radiation. The unit of this instrument is again watt per meter square. Dear learner, now we will understand the solar radiation spectrum, which can be classified on depending on the wavelength of, or you can say type of the light. So first is ultraviolet rays. It covers the wavelength range of 100 to 380 nanometer on the solar spectrum. It is invisible to the human eyes and has the most serious effect on the skin in the form of sunburn. It is divided into three bands. First one is a ultraviolet C band in the range of 100 to 280 nanometer. Second one you can say ultraviolet B in the range of 280 to 350 nanometer, and third one is ultraviolet A. The range of this particular band is 315 to 380 nanometer. Now we will understand what is visible light. The visible light covers the wavelength range of 380 to 750 nanometer. The longest visible wavelength is of red color. The range of this particular red color of longest visible wavelength is 650 to 750 nanometer, and shortest is of violet color, that is range comes between 380 to 450 nanometer. Now we will understand what is the infrared region. Its wavelength range is from 750 nanometer to 1 nanometer. It accounts for a significant portion of the solar radiation that reaches the Earth's surface. It is further subdivided into three parts, that is infrared A, and range of this infrared A is 750 nanometer to 1400 nanometer. Then second one is infrared B. The range of this infrared B is 1400 nanometer to 3000 nanometer, and third one is you can say infrared C, and this range of infrared C is 3000 nanometer to 1 nanometer. Dear learner, now we will understand solar radiation on a surface. So first of all we will understand the basic principle. Each location on the earth receives sunlight at least for a part of the year. The amount of solar radiation that reaches a particular spot on the earth's surface depends on number of factors. And what are those factors? First factor is geographic location. Second one is time of the day. third one is what is the season, then local landscape, as well as it will also depend on the local weather condition. The sun strikes the surface at different angle ranging from 0 degree, which is called just above the horizon, or to the 90 degree, and this 90 degree angle is basically, you can say, just directly on the overhead. Due to the nearly round shape of the earth, when the sun rays are vertical, the earth's surface gets maximum energy possible. The more slanted the sun rays are, the longer they travel through the atmosphere, the becoming more scattered and diffused, reducing the amount of energy reaching earth's surface. Earth revolves around the sun in an elliptical orbit, and it's closer to the sun during a part of the year. When the sun is nearer to the earth's surface receives a little more solar energy. The earth is nearer to the sun when it's in summer in the southern hemisphere and winter in the northern hemisphere. The 23.5 degree tilt is the earth axis of the rotation, is also a significant factor in determining the amount of sunlight striking the earth at a particular location. The rotation of earth around its own axis is responsible for hourly variation in sunlight. In the early morning and late afternoon, the sun is at low in the sky. Its rays travel longer through the atmosphere than at noon, when the sun is at its highest point. On a clear day, the maximum amount of solar energy reaches on a solar collector around solar noon. So dear learner, before we discuss solar radiation on a surface, horizontal or tilted, let us talk about the nature of the solar radiation. The earth receives two types of solar radiation called beam and diffuse radiation. So now we will understand what is this beam radiation or direct radiation. So beam radiation or direct radiation can be defined as it is the portion of the solar radiation that does not get absorbed or scattered in the atmosphere and instead reaches directly. If it is interrupted by an opaque object, it casts a shadow. Now we will understand what is the diffuse radiation. The diffuse radiation is received by the earth from all directions. The radiation may change their direction due to the scattering from the dust particles, clouds, etc. while passing through the atmosphere. Diffuse radiation do not have unique direction. The diffuse radiation here you can see in the diagram also. So the concept of how beam and diffuse radiation are received by the surface is shown in the figure. The diffuse component of solar radiation, which is denoted as capital B, is that portion which is reflected from the cloud, the ground and the nearby object, and direct component of solar radiation is denoted as capital A, is that portion which falls onto the flat plate solar panels. So some of other terms used to discuss the solar radiation are, that is called global radiation, or you can say solar insolation. So the total radiation is the sum of direct radiation and diffuse radiation, which is called global radiation or simply insolation. So dear learner, now we will understand what is this particular term that is called insolation. Total amount of solar radiation per unit area per day reaching a part of the earth is called insolation, a short form of incident solar radiation. The solar insolation is defined as the amount of sunshine incident on the surface of earth per unit area per day. You can determine the size of solar collector provided the value of solar insolation is known. If the value of solar insolation is less, the area of collector will be large as compared to the case where the solar insolation is high. Solar insolation is expressed in kilowatt hour per meter square per day. It is the amount of solar energy which falls on a square meter of earth surface in a single day. just you have to remember that 1 kilowatt hour per meter square per day is equal to 3.6 megajoule per meter square per day, which comes equal to 317.1 British unit per foot square per day. Or you can say 1 kilowatt hour, or you can say 1 unit of electrical energy is equal to 3.6 megajoule, or you can say 859.8 kilocalorie, or you can say 3412 British ton. Now we will understand another term, that is called irradiance. The rate at which radiation fall on the surface per unit area is called irradiance, and it is measured in watt per meter square. In solar energy engineering, we come across the term extraterrestrial solar radiation and terrestrial solar radiation. In order to understand this term, let us consider terrestrial and extraterrestrial region as shown in the figure. So here you can see the top one is sun and lower one is earth. So between sun and earth there is a three region. One is extraterrestrial region, then second is atmosphere, and third is terrestrial region. So here you can see in the extraterrestrial region following components are there, like oxygen, carbon monoxide, hydrogen and dust. And similarly in terrestrial region you can see the diffuse radiation and long wave radiation which emits from the earth has been shown here in this figure. Now we will understand extraterrestrial solar radiation. You know that earth is inclined at an angle and revolve around the sun in elliptical orbit. The orientation of earth's orbit around the sun is such that earth sun distance varies only by about 1.7%. The solar radiation outside the earth's atmosphere is almost constant and is called constant. Solar constant. This term is very important that you have to understand. The radiation received per second by a surface of unit area held normal to the sun rays at the mean earth sun distance outside the atmosphere is constant throughout the year. It is called solar constant, and this value of one solar constant is equal to 1367 watt per meter square. So generally this question is asked what is the value of the solar constant. So just you have to write the one solar constant is equal to 1367 watt per meter square. Here you can see the intensity of extraterrestrial radiation measured in plane normal to the radiation. This formula is given by the Duffy and Beckman. So this formula can be written as I extraterrestrial is equal to I extraterrestrial multiplied by 1 plus 0.033 cos 360 small n multiplied by 365. So here you can see that ISC is nothing but it is a solar constant, and this small n is denoted as day of the year. So suppose we are talking about the January 1, so you can say the value of this n is 1. If we are talking about like January 31, so what would be the value of n? This value would be the n is equal to 31. Now we have to understand what are the main feature of the solar radiation. So you know the sun is continuously radiating energy in form of the electromagnetic radiation. These radiation while passing through the earth's atmosphere are subject to absorption by the ozone, oxygen, nitrogen, carbon dioxide, carbon monoxide and water vapor, and this scattering is by dust particles, air molecules and water droplets in the atmosphere. So here you can see the fraction of radiation striking the earth's surface is reflected back into the atmosphere, where it is again absorbed and scattered. The remaining radiation are absorbed by the earth's surface. So just you have to remember that X-ray and extreme ultraviolet radiation are absorbed by the nitrogen, oxygen and other atmospheric gases. Second point that you have to remember that ozone absorbs ultraviolet radiation and the wavelength which is less than 0.4 micrometer. Third point that you have to remember, that water vapor absorb infrared radiation. So what is this infrared radiation? That have wavelength greater than 2.3 micrometer. So the main component of solar radiation falling on the earth are the following. One is short wavelength radiation from the sun reaches to the top of the atmosphere. Second, cloud reflect 17% back into the space. If the earth gets more cloudy, as some climate model predicts, more radiation will be reflected back and less will reaches the surface, and 8% is scattered backwards by the air molecules, and 6% is actually directly reflected off the surface back into the space. So the total reflectivity of the earth is 31%, which is technically known as albedo. So during the ice ages, the albedo of the earth increase as more of its surface is reflective. Now we will understand monthly average of daily solar radiation on the horizontal surface. The computation of the solar radiation on a horizontal or tilted surface is not an easy task and requires a complete knowledge of solar geometry and the Earth-Sun relationship. However, there are correlations available for the estimation of solar radiation at horizontal surface. Ultimately, we need the value of the monthly average of daily solar radiation on horizontal surface. So the correlation for determining the monthly average of daily solar radiation on horizontal surface is given by the following relation, which is denoted as H upon HA is equal to A plus B multiplied by small n upon capital N, where this capital H is nothing, it is monthly average daily total radiation on a horizontal surface. And this H naught is nothing, it is a monthly average daily extraterrestrial radiation on a horizontal surface, and this small n is monthly average daily hours of the bright sunshine hour, and this capital N is monthly average of maximum possible daily hours of the bright sunshine hour. And the A and B are the regression parameter and are given by this following expression. Here you can see this expression, where this phi is a latitude and E naught is a elevation of the location above the sea level in the kilometer, and value of this latitude and elevation of the location above the sea level is in the kilometer. So just you have to see this formula, how you will calculate this value of a small a and small b. In this table here you can see the latitude and elevation of some places in India are shown, like Bangalore, Mumbai, Jodhpur, New Delhi, Shimla and Chennai. Suppose you are going to experiment for particular city, like suppose we are going to experiment for the New Delhi. So just you have to remember what is the latitude and what is the elevation. So this table will be very useful when you are going to calculate the some parameter. So just you have to remember this formula, or you can note in your notebook. Now we will understand solar radiation on a tilted surface. So let us consider the solar radiation falling on a surface. The amount of solar radiation on terrestrial surface at a given location for a given time depends on the orientation and slope of the surface. A surface which is always normal to the sun's ray would be receive maximum amount of solar radiation. The solar energy collectors may be tilted at the suitable angle so that it is roughly normal to the sun's rays, so that maximum energy collection is obtained. If you wish to design any solar energy device, you need to know the data of solar radiation on such tilted surface. However, measured or estimated radiation data are available mostly either for normal incident or for horizontal surface. So it is necessary to convert this data to radiation on a tilted surface also. So now let us consider beam radiation falling on a horizontal and tilted surfaces as shown in figure. So here you can see in the figure where this IBN is a beam radiation on the normal incident, and this IB is a beam radiation at horizontal surface, and the third term IBI is beam radiation at tilted surface. So from this figure you can note down this I suffix b is nothing, it is equal to IBN cos z, and IBI is IBN cos I. So the beam radiation tilt factor R suffix b is then given by RB is equal to IBI upon IB, or you can say it is the ratio of cos I to the cos z. So our tilted surface receives diffuse radiation as well as reflected radiation from the ground and surrounding in addition to the beam radiation. The diffused sky radiation on tilted surface at an angle is given by ID multiplied by 1 plus cos s divided by 2, where ID is the diffused sky radiation on horizontal surface. So if the ground and other surfaces seen by the tilted surface have a diffuse reflectivity tau z for the both beam and diffuse sky radiation, the amount of ground reflected solar radiation or tilted surface is equal to tau z multiplied by 1 minus cos s divided by 2 of the total radiation, that is IB plus ID on the horizontal surface. So the beam diffused and reflected component can be added to give the total incident radiation IT on a tilted surface, and the total radiation on a horizontal surface I is the sum of horizontal beam and diffused radiation. So dear learner, what we have studied so far, the major portion of the energy of the thermal radiation lies in the range from approximately 0.1 micrometer to 100 micrometer, and the visible portion of the thermal radiation range from approximately 0.4 to 0.7 micrometer. The electromagnetic radiation behave like wave as well as particles. The electromagnetic waves are made of small discrete quanta called photons, which travel with the speed of light. So learner, in today's session we discussed heat transfer characteristic of the surface, then we have discussed radiative properties of the real surface, and after that we have discussed or understood the concept of the solar radiation, and after that we have discussed how to estimate solar radiation on a horizontal surface and a tilted surface, and you were able to understand the main feature of the solar radiation. So learner, in the next session we would discuss the topic which is related to the solar cell parameter, working of the solar cell or photovoltaic effect. Then we will understand different types of the solar panels, type of the photovoltaic cell, and again we will be able to understand how we will define the photovoltaic array. That means in the next lecture we will focus on only the solar photovoltaic phenomena. Thank you very much.